Hello world, this is the computer science man, and today we're going to start with the paper 2 component of this course. I've thought of studying the practical part because, we just started with the theoretical yesterday, but if if we do it simultaneously, it will be easier to finish, quicker to finish the syllabus, as well as we'll have a break from theory now and then because practical is the fun part of the CS, where theoretical is just the understanding part. So now and then we can switch it up. And so we're going to start with the first unit in the paper 2 component, and that is computational thinking skills. So, what we're going to learn is we're going to understand computational thinking and the techniques that come under it. Okay, so let's get started. So, we need to first understand what computational thinking is. Well, in simple terms, it's just a method. So it's just a method to solve or to study a problem. So first we need to study a problem, method to study a problem, method to study a problem, and to formulate an effective solution, right? So then after doing this, we need to convert this in a way, or we need to make it in a way that the computer can also use it. Okay, so first of all we need to understand, so humans need to understand first, right? We need to understand the problem, and we need to find a solution. Need to find a solution that computers can execute. That is the crux of computational thinking. And underneath this method, there are many techniques that can be used to make computational thinking easier. Okay, so the first method, okay, let me just list out all the methods. Sorry, the techniques. So the first technique is abstraction, and the second is uh, decomposition. Decomposition. Pattern recognition. Lastly, the use of algorithms. So I'm just gonna write algorithm. So these are the methods that we will look into for this course. And first of all, but this doesn't have to be this order. This is usually how we follow it. We start with abstraction, then decomposition, then pattern recognition. Then lastly we write an algorithm. We design an algorithm so that a computer we can represent a solution so that we can convert it in a way a computer can understand. Okay, so we're gonna start with abstraction. So abstraction. So what is abstraction? Well, in we can say it. I mean, just looking at the word, it's basically. Uh, so I'm just gonna give you like a brief, statement about it. So it allows us to deal with complexity. Okay. So when we receive a problem, or when we identify a problem, the first thing that we want to do is we need to break down what's important to solve the problem, right? We need to find out what's the cause of this problem. So that's what abstraction is. It's the process of extracting information, which is essential to solve the problem. Okay, we need to ignore anything else that is irrelevant to solve any problem, right? We just need to find the information, like extracting the information which is only useful for the uh production of the effective solution. Okay, so abstraction is, um we need to extract only relevant information. Okay, we need to ignore if it is not required to solve the problem. Okay, so that is what abstraction is. So, for example, let's say you have a roadmap or like a train map. Okay, so for this, let's say you want to go from town A, so you want to go from town A to town B. Okay, let me say there's town C as well and town D, and then you have a, I don't know, a railway line between these towns. Okay, so between these towns you have a railway line. So it goes like this, goes like that, and it also goes like that. Okay, this is a random railway line. So for this in a map, there's many types of map. You can take a satellite map of this. You can take just, not without the train routes. This is the train route map. Okay, so for us, the goal is to find a route train using a train from town A to town B, right? So we need to find a route from here to here. This is our end destination. So we don't need to know about the terrain surrounding this area, or if the train is underneath or above or just normally ground level. We don't need to know that. We only need to know how to, just the route from town A to town B. Which station should we get on and which station should we get off? That's all we need to know. We don't need to know about the other unnecessary information, such as what's the traffic on the road or what's the weather like. We just need to know if we can go from here to there. That's all we need to know, right? So we're just leaving out any unnecessary information which is not required to solve for a given problem. That is what abstraction is. As I said, initially, it allows us to deal with the complexity of a problem. Okay, that's what it essentially does. It allows us to deal with the complexity of any problem. We can reduce the complexity. We don't need to consume a lot of information to just solve a simple problem. We just need to know the essential information. That is the first step of solving a problem. We only need to collect necessary information. That is the first step. That's why we say it allows us to deal with the complexity. Okay, so moving on, next is decomposition. So decomposition, what it is, it's nothing. It's clearly in the name. Decomposition. So decomposition is the breaking down of a complex problem. So it's the breaking down of a complex problem into a smaller problem. So we're breaking down a complex problem into a smaller part or problem, smaller part or smaller task. So we can into a smaller part. So this, initially we don't need to break it down like initially just to one time to a smaller part. We can do it multiple times. So into a smaller part and even multiple times to a smaller part until until the problem is very simple and broken down to understand. That is decomposition, okay? Broken down to understand. So that is decomposition. It's just the process of breaking a complex problem into smaller parts, okay? You can break it down into more smaller and smaller and smaller until it's easy to understand. It just depends on your personal understanding, okay? So that's decompose. For example, let's say you're given the task to make a simple calculator, not a scientific calculator, just a calculator that can add, divide, multiply, and subtract. So at first that seems like a big task, right? But let's say you can break it down like first, for example, let me give you an example. So, for example, you're given the task, make a simple calculator, cal- which can add, subtract, multiply, and divide. So this is your task, right? So the first step you need to do. So you want to break down this problem into simpler problem. So the first problem, I mean, the small part, you need to get input. So input, you can break it down, just the input part. So you need to get some numbers, or like, for example, just two numbers from the user. Okay, we're broken down the input, the first part of this problem. Then we need to identify which operation to carry out. Is it which operation to carry out? We need to know if we want to carry out addition, subtraction, multiplication, division. This also we need to get from the user. Then we need to perform the calculation. Perform the calculation. Okay. And lastly, we need to output the answer. So this is just a simple breakdown of the problem, right? We can also break it down into different operations. So we can do it as plus, then minus. Each of them can have a different steps. We can branch it out. So one per, like we can initially focus on the addition first, then subtraction, then multiplication, division. So we're breaking down like a large problem into smaller pieces. So, for example, the phrase, they say you can't eat an elephant as a whole, right? You have to cut it into smaller. I mean, you're not going to eat an elephant, but just just saying, like a saying, you got to cut it into small pieces, and then only you can eat it. You can remember decomposition like that. So, from decomposition, you can connect this to pattern recognition. Okay, so the next part is pattern recognition. So you can connect this with pattern recognition. The reason why you can connect this with pattern recognition is because, for example, let's take the calculator example. So here I said to make a simple calculator. Let's say the uh, I'm gonna add the how to say it. I'm gonna add one more task in that calculator, or like one more feature, right? So the feature can now carry out. I also want it is exponentiation. So I want exponentiation to also be carried out for the calculator. So here, what is exponentiation? For example, you have a number or variable a, and if you raise it to the power x, this variable is multiplied x times. Right? So a is multiplied x times. That is what it is. So here you can see the common thing. So here it's also multiplied, and we also have a multiplication operation. So we can connect these both, and since it's the same, we can use it, like we can reuse the same operation to carry that. That's a small difference, but while we're calculating it, it's still multiplication. So for that, we can use the same operation that we used here. So this reduces I mean, we don't need to find another solution for this problem as well. We can just use an existing solution for another problem. So that saves us time. That is one of the major advantages of pattern recognition. This saves time, and this saves time and space. Like, we don't need to rewrite another algorithm for pattern recognition, right? Speaking of algorithms, we're going next to algorithms. So algorithms this algorithms, what they basically mean, let me just give you an introduction. We'll dive deep on algorithms in the next video, but simply saying, algorithm is just a sequence of defined steps, that can be carried out to perform a task. That is what an algorithm is. So, previously we performed all these actions, right? So, if we consolidate all these actions together, we can write that as an algorithm. This can be later converted into, program code such as Python code or C sharp, C plus C. We can convert that so we can run it on the computer, or our solution. Okay, so this is what an algorithm is. Okay, so let me just talk about the advantages of abstraction and the benefits of decomposition and abstraction. So one of the benefits of abstraction is, let me just take this down here. So benefits, right? So benefits of abstraction. So one of the benefits, some of the few benefits part of abstraction is, so remember the map example. So we just need to know the route. We don't need to know about the terrain. We don't need to know about the road traffic. So nothing, right? So we save time. So same thing here. We save time. That's a common thing. Usually, if we want to make an effective solution, the saving of time is the number one priority we should give. Okay, if we solve a problem faster, let's say you're the head of a company and you have a problem, and you're giving out this as a task to your employees, like to teams of employees. So you're probably going to select which solution executes faster, right? So whichever solution that's performs faster, you're going to select that, because you don't want a solution that's slow. You want it to be fast. You want to be solved quickly, right? So that's one major advantage of abstraction. You don't need to filter out the irrelevant. Already filter out, right? So you don't need to do that again. So because of that, the time taken to develop a program is reduced. That's also a big win, right? If it's reduced, yeah, it's great. And on top of that, for example, you have an app, right? So on the train app, right? You want to satisfy your customers. You have an app, you want people to use it and be happy with it, right? So if you're gonna add so many extra features, people are gonna be like, no, why do we need this? We just need to find a train route, right? So that's also a benefit of abstraction, right? It's because you're focusing on focusing on key features. Customer satisfaction will be high. Sorry for my bad handwriting. I need to improve. Customer satisfaction will be high. Okay, so advantage of decomposition. Well, I mean, it's pretty straightforward. Again, it's going to save time rather than just breaking our head up on a complex problem. We can save time, and we can split the tasks into multiple teams, right? For example, in a company, there's many people, right? So you can give each team a task. So again, which is saving time, and it will be easier to understand. So easier to understand, right? So yeah, easier. Easier to understand. So that's also a benefit of decomposition. Pattern recognition. Yeah, you don't need to reuse the same algorithm. We can reuse the same solution for a different problem. So initially, if we had a problem, we can reuse the same solution. That's also a benefit of pattern recognition. So up till now, we just focused on the four main pillars of computational thinking. And just as a summary, we'll go through it, just 1 minute summary. So what is computational thinking? It's just a method to study a problem, and we need to formulate an effective solution for it. So, and from this, we need to make the computer understand how to compute it, and how it's going to be computed, and what needs to be computed for this problem. So yeah, we need us humans to understand, and then we need to find a solution that computers can execute, and that we can use it in later in the future. That is computational thinking. And the four main pillars are abstraction, decomposition, pattern recognition, and the writing of or defining of algorithms. And abstraction is basically filtering out information and only collecting what is necessary to solve the problem. Decomposition is breaking down a complex problem into smaller and smaller parts until it's easier to understand or find solutions to. Then there's pattern recognition, which basically is used to uh, identification of problems that can are similar and they can use the same solution. That is pattern recognition. And algorithm is just this, just like a steps, or like, for example, you have a cookbook. There's steps to follow to cook a dish. Same like that, an algorithm is just a sequence of steps that can be carried out to perform a task for the computer to perform the task. That is basically it for now. Next class, we're going to deep dive to algorithms. We're going to start with pseudocode, flowchart. I'm going to use I'm going to teach pseudocode where we can solve example questions with after learning pseudocode based, past papers. Then for theory part, I'm going to post a video probably by tomorrow, continuing the binary chapter. You can just do that. So so that's it. That's for the video. So let me know any advice, how I can teach my how I can change my teaching methods, and if I need to work on, I stutter sometimes, so I need to work on that as well. And if I need to make my notes more interactive, and if you guys like my notes, I can write it in a neater way and provide it for you guys to refer later during your exams. Just let me know any suggestion you have, or what topic you guys want to go next, so I can start on another video that we can do simultaneously 3 or more chapters as well if you want. Okay, so yeah, that's it for now. Thank you guys. I will see you next time later. Thank you.